Engineering. It's the backbone of every leap forward. It's given us skyscrapers to the clouds, computers in our pockets, and even a man on the moon. The lifestyle we have created through engineering has changed almost every aspect of our lives, and for the better. With all of these new technologies, though, sometimes it doesn't go according to plan. Materials fail, flaws are oversighted, and low budgets create subpar products. Now, if you're talking about an electric fan and its motor stops working, that's not that bad. Oh no, I'm going to be slightly warmer now until I buy a replacement. It's when the large feats of engineering fail that it really becomes a problem. The worst failures violate ethical codes, destroy the environment, crash economies, and even in some cases, take lives. As engineers, we must learn from past failures to ensure the safety of the public while still leaping forward.
Completed in 1952 in the Henan province of China, the Banqiao Dam was the flagship of 62 dams built during China's Great Leap Forward. The dams were primarily for the use of water retention for farmlands nearby, with flood protection as a secondary use. As the dam was being built, Chen Xing, the head engineer, whistle blew on the construction. He said, A, water retention as a first purpose is short-sighted and dangerous, and he backed it up with data, and B, the dam should have 12 sluice gates. He was removed from the project. Only 5 sluice gates were built. Cracks immediately started to form upon completion. This worried the Chinese people, so Soviet engineers were flown down to reinforce the dam. So everything went fine, right? Wrong. Enter Typhoon Nina. The projected annual rainfall for the region was about 800 millimeters. The typhoon rained over 1,000 millimeters in a single day. The max amount the dam could release with its 5 sluice gates was 3,092 cubic meters per second, when the estimated average of the influx of water was almost 8,000. Of course the dam broke. While one might think the village just past the dam was in danger, in reality, most of those people were evacuated quickly. The crew manning the dam were able to communicate it to the immediate area, and the population got away in time. What really ended up being bad were the populations living downstream. The breaking of the Banqiao Dam culminated in a domino effect, bursting several other smaller downstream dams. Whole houses, and in one case an entire village, were washed away by an ever-growing flow of water that became more devastating as it traveled. With an event so terrible, how in the world have not many people heard about this? Because it's publicly acknowledged that the Chinese government covered it up until the 1990s, almost 20 years after the fact. So let's see which codes were primarily upheld by whistleblower Chen Xing and which were broken after his removal. The employer and authority are both the government. So when Chen Xing thought the dam would fail, speaking to the government and the public was the right decision to make, upholding codes II.1.A and III.1.B. The subsequent building of the dam with acknowledged errors by the government, who is the employer and the authority, breaks all sorts of codes. They knowingly built a dangerous dam, slandered Chen Xing and removed him, assured its strength to the public, all to get the dam built and save on some budget for the government. That's 1 through 6 of the fundamental canons right there. They actively removed any dissent to the project, breaking specific code II.1.A, and after the disaster, they covered it up. That breaks code III.3.A. So how bad was the damage? The Chinese government initially said 26,000 people had died. After more information was revealed in the 90s, that number jumped to 85K to 240K. It collapsed millions of homes and displaced 10.6 million people. One harrowing account of the recovering affected population was quoted. The year after the disaster, in early summer of 1976, the fertile land where the victims were buried produced a bumper crop. Surveying the land carefully, one could see crops everywhere, but what made people's hearts quiver were the small areas where the crops were especially rich and dense.
Our most recent engineering disaster is one that is more known, but even though some people have already heard about it, they might not know the details to what actually happened. The tragic disaster of the Deepwater Horizon oil rig affected not only the people that were on it, but also affected the ecosystem around it. The reasons why we chose this engineering disaster is because it gives us a good look at how following ethical guidelines will always result in the safety of others and a better outcome of the job being done. There were many different actions that took place that led to the cause of this disaster. Well site leaders making the wrong decision on tests, the company using cheaper parts, safety mechanics not wired correctly, and rush procedures that were not done correctly are all reasons that are responsible for people's lives and animals' lives. A prominent mistake that took place involved a safety device that was not working correctly. The rust insulation of the lockdown sleeve during the abandonment process resulted in a failed test that was deemed to be successful. These tests showed that deep in the drilling pipe, there was a buckle in the pipe due to pressure that was not supposed to be there. By not recognizing this problem, all the lives that were on the oil rig were put in danger.
The immediate effects following the disaster: 11 men were killed, oil had spilled and leaked all over the Gulf of Mexico, and its surrounding ecology was critically damaged. As we can see with the images in the sea, oil is streaked across the ocean floor. The other images show the state of wildlife due to the oil spill. The code violated at I Section 1 was obviously not upheld due to the negligence towards the rig. Safety was not upheld for the people working on the rig or the ecology. Because BP chose to cut corners and use a lesser quality spacer that had different volume and composition, the explosion happened. Eventually, the pressure built up and the drill pipe buckled. There were even 0 pressure tests beforehand that failed. The first test, they thought it was due to a loose seal in the drill pipe with a blowout preventer. The second test, they tightened the seal, and yet there was still a rise in pressure with a huge backflow of oil. III.1.A wasn't upheld either due to the CEO trying to downplay how much oil was being spilled into the ocean. His defense was that they couldn't accurately calculate the spillage into the ocean. However, he tried to play it off as less than it was. During an interview, he even heartlessly said he wanted his life back from all the ensuing chaos of Deepwater Horizon.
The Deepwater Horizon disaster created devastating long-term effects. Overall, the leak summed up to be more than 206 million gallons of crude oil, which translates to about 3 million barrels of oil. To add on, this disaster proved to be a costly cleanup, with an estimate of a $60 billion cleanup cost and still counting. Furthermore, the leak dealt extreme damage to wildlife in the area. One can find a variety of photos displaying poor oil-covered animals. These animals are suffering from lasting diseases and ultimately could take the populations decades to recover. Why is it important to study these disasters, one might ask? It's important that we take the time and learn what caused these events to help prevent them in the future. After investigating the Deepwater Horizon failure, the mechanism that caused the rod to buckle, leading to the overall disaster, was called effective compression. When there is a large difference in pressure between the inside and outside of the pipe, it creates a very strong bending force. This was a very crucial finding. The same conditions that could possibly cause an issue were discovered at other drilling rigs. And that concludes our presentation. Group 4 would like to thank you for watching and hope you took away some valuable information.